of logarithms, which is where students start to lose logarithms, but always keep in mind that a logarithm is the inverse of the exponential, and so logarithms solve for exponents. So logarithms themselves are exponents, and then, so they follow all of the properties of exponents. And so that's the first thing we're going to look at, the properties of law of exponents. We're going to use them to combine or expand logarithmic expressions, and then we're going to talk a little bit more about the change of base formula. So remember, a log function is true if or only if that inverse equation is true. M and N and all of these laws are always algebraic expressions or real numbers that are always positive, right? I can't have 0 and I can't have negative, so we're going to assume that all of them come out positive. Right, so the first property is the product property of logarithms. Right, and equality means it goes in both directions, and we are going to use it in both directions. So when I do an example, I'll do an example in both directions. Right. And I did base 10 because it's just the easier one to type out. But it would be true for any base. Base A, base 2, 5, natural log. All of them hold true to the same logs. I just chose base 10 to show you because it's the easiest one to type out. All right, so I have a log of an expression times another expression. All right, and that's inside my log. It's the log of m times n inside is the same as the log of m inside plus the log of n inside. All right, so again, when I have my log of the same base and I have something inside multiplied out, I can expand it into an addition of those two numbers. Or vice versa, if I have an addition in the same base, right, it's the multiplication. And where that comes from, just to sort of give a room of reference, right, if I've got 10 to the x times 10 to the cubed, it's the same as 10 raised to the x plus 3. That's where we're coming from here. Right? If I've got the same base and my exponents multiply with the same base, well, I'm adding those exponents. And that's a little abstract to think about it that way, but that's the essence of it. All right, let's do it with logarithms, though. All right, so again, I'm going to do a different log. I'm going to do the natural log. So if I have the natural log of 3 times x, I can rewrite, if I want to, into the natural log of 3 plus the natural log of x. Or the other way around, if suppose I've got log base 2 of 5 plus log base 2 of 3, well, I can rewrite that as a single log. Log base 2 of 5 times 3, which would be log base 2 of 15, which that I can use my change of base and find it. So that's why it's helpful to be able to go both directions. I should be able to expand, right, which is the first direction. I'm expanding my logarithm from one logarithm to 2. In my second one, I'm compressing. I had 2 logarithms and I compressed it to 1 because it makes it easier to work with. Alright, so that's the product property of logarithms. The quotient property of logarithms is if I have an expression or a number divided by an expression or number inside the log. It's the log of a division. I can separate the division into the log of m minus the log of n. Right, but if you'll notice, the m and n are inside my log. And again, it comes from the same idea as their exponents, and I'm not going to go through that, but the reason why this is true is because they're exponents. Right, so to do an example, if I did the natural log of x divided by 2, I could rewrite that as the natural log of x minus the natural log of 2. Or vice versa, if I had the log base 8 of 10 minus the log base 8 of 5, I can rewrite that as a single logarithm. Log base 8 of 10 divided by 5, which is log base 8 of 2, which then I can use my change of base and solve that. So again, equality means I can go in both directions. The first direction is expanding it. The second direction is compressing it. All right, I can either expand it into multiple logs, or I can compress it into a single log. So expanding it is what you'll be using if you go to calculus, because it'll be much easier to do calculus on the expanded form. When we're solving, though, a lot of times we want to solve it and we want to contract down to one logarithm. All right, so I'm going to go to solve stuff. the second way we like to write it out. Alright, so that's the quotient property for logarithms. The power property. Alright, we like this power property because it allows us to get rid of a power, solve per power. So this is very helpful when we go to solve stuff. Right, so what it means is if R would be some power, some number, real number, so R stands for a real number. So, and it's m raised to the R. Alright, so it's a little, again, I kind of wish that they had written it, I'd written it with the MR inside. So it's something like this. So if I have log of x cubed, I can rewrite that as 3 log of x. Or if I had the natural log of 2x plus 1, I can rewrite that as x plus 1 times the natural log of 2. Right, which helps us out when we go to solve stuff because it gets rid of the exponent. I can work in reverse too, right? If I've got negative 2 times the natural log of x, I can rewrite that as the natural log of x raised to the negative 2. Right? Or if I've got 5 natural log of 3, I can rewrite that natural log of 3 to the 5th, right? Which that I can then solve. Alright, so that allows us to manipulate expressions a little better. Alright, so just a reminder of the uniqueness property once more time, specifically with logarithms. So right now it's a property of logs. We already talked about this in the previous set of notes. It's the same uniqueness property, but I just wrote down the log example. Alright, if I have m equal to n, then I can take the log of both sides, and it's still the same, or vice versa. If I have the same log of both sides, that means those inside numbers should be the same, which we talked about that in the last example. Alright, the next set is some examples where we're going to go through and test to see if they're true or false, and I'm going to do that in the next video.